Hello and welcome to Physics 262 Pre-Lecture Notes. I'm Dr. Steve Brule. In today's lesson we'll study dielectrics. We'll find out why the electric field is reduced when an insulating material is inserted between the plates of a capacitor. We'll use John Lennon's equation to show why the insertion of a dielectric results in a smaller potential difference between the plates and thereby a greater capacitance. We'll learn how the dielectric constant is used to calculate the capacitance as well as the attenuated electric field. We'll discover how the demand for rare conflict minerals in developed countries has led to political instability and environmental degradation in Africa. And we'll use the dielectric strength to find out the maximum charge a capacitor can hold before breaking down. And finally, we'll learn how the changes in stored energy can be used to find out whether a dielectric gets sucked in or pushed out of a capacitor. All right. First, let's consider putting an insulating material between the two plates of an isolated capacitor that's charged up. What would happen to the electric field between the plates? Well, let's see. If we put a material in here, then what's going to happen is charge is going to want to flow since there's an electric field present. So electrons will be attracted to this side of that material and protons will be left on the other side. In other words, it has become polarized. That material has become polarized. And the induced charge that we see here in this blue material, these are the charge densities of the induced charges in the insulation material, and the induced charge creates an electric field in the opposite direction as the electric field that's created by the charged plates that are already charged. So we had an electric field that was going to the right, but now we see the electric field is attenuated because there's some electric field induced in the opposite direction from the charge that has been induced on these inside the insulating material. Well, if the electric field is decreasing when we put in that insulator between the plates, what happens to the capacitance of the capacitor? Well, as John Lennon has pointed out so many times in so many songs, the difference between the potential between the two plates is equal to the electric field dotted with ds, with the negative sign. We know why that's there. And let's see. So if the electric field is smaller, then the change in potential is also smaller. And if the change in potential is smaller, then we're going to end up with a larger capacitance because of Hitler's equation. So this is how we can create a capacitor that has larger capacitance than just two parallel plates. We insert a dielectric material in there. Oh, well, it's a insulating material. Amount of increase achieved depends on how much capacitance we get increased here. Depends on how much this material that we stick in between the plates is polarized. So the more polarizable the material, the higher the capacitance. And you might think, well, if I put a metal in there, it's totally polarizable, but then it would just conduct charge from one plate to the other. It has to be an insulating material that allows polarization. Okay, so we call any material that's put in that's an insulating material that's put in between the plates of a capacitor, we're going to call that a dielectric. And we tabulate the dielectric constant of different materials according to how much they're polarized once they're placed inside an electric field. So we get the capacitance. If you have a parallel plate capacitor, the capacitance with the dielectric is equal to this dielectric constant times the capacitance that you get without the dielectric in there. And we see many different materials, Teflon and silicon oil. This one is pretty high here. Strontium titanate. All right, so what's this over here on the table, the dielectric strength? Well, that is the maximum electric field. This is the dielectric strength is really an electric field strength, which is in newtons per coulomb or as it's shown here in volts per meter. So it tells you how much electric field this material can withstand before it suffers what we call dielectric breakdown. And that's what happens when with air, when we have a very large electric field that's developed through a charged cloud, and the ground is charged positively here. What happened? Charged positively. Sorry, I keep hitting that button. So there's this electric field, and when the electric field for air, let's see what air is. It's 3 million volts per meter. So when we get more than 3 million volts for every meter of distance between the cloud and the Earth, then the air can no longer withstand the incredible electric field, and the electric field actually rips air molecules apart and then allows the charge to start conducting. And that's what happens in any dielectric material, and we have to worry about that, even paper or whatever. We don't want to have dielectric breakdown in our capacitor, because then the capacitor conducts and it's no longer a capacitor that holds charge. Well, let's start with a little problem here. Let's find the capacitance of a parallel plate capacitor filled with mylar that has an area of 1 square meter, you know about how big that is, and a separation of only 2 millimeters. Well, we'll find the capacitance in the usual way. Here's the equation for the capacitance of a parallel plate capacitor, but now we're going to multiply by this kappa, the dielectric constant, to find, which is 3.2 for mylar. So we get a capacitance that's more than what we would have had we not had the mylar. We're able to get larger capacitances using electrolytics. Those are like oils that go between the plates. Generally, the electrolytic capacitors also leak worse than a regular capacitor. They allow charge to flow from the two plates, which is not something we want in our capacitors. Well, it turns out there's this fantastic element, it's called tantalum, and it has the most wonderful properties for capacitors. And this is a capacitor we used in class to store charge. So here's this small thing. It's about as big as the top to a ketchup container. You know, it's not so big, yet it's got 1 farad of capacitance. That's an incredibly huge capacitance for such a small capacitor. The problem is that tantalum is very rare, and most of it is found in Africa, and we refer to it as a conflict material because it's not just there's international agencies that have branded tantalum as a conflict material because it's mined in Africa, and the proceeds from this very expensive mineral that is mined there are then used to finance dictators and wars in Africa. So there have been movements to try to limit or completely eliminate the use of these rare materials because of the kind of chaos they're causing in particularly the Congo. They're also very detrimental to the environment because when you're mining this mineral that is just in the crust in very trace amounts, it's very hard. You have to mine a tremendous amount of material, and then to refine that material, you have to go through and get rid of all the other stuff, and it creates a lot of waste. And it just so happens that it's the places that have the most rare earth materials happen to be very precious ecosystems in Africa with endangered species. Okay, so we use tantalum and many other rare earth materials in our cell phones and computers, in our cars. We're using it in all kinds of devices. So scientists are looking for other materials that could do the same job. All right, well, what's the maximum charge that a parallel plate capacitor with mylar could hold? Well, now we're going to worry about the dielectric strength. So in order to find the maximum charge, you have to assume that you're getting the maximum E field. Well, we already know what the capacitance of this capacitor is. We can calculate the electric field by, normally you would say the electric field in a capacitor is sigma over epsilon naught. But remember how the electric field is attenuated when we insert a insulator between the plates, and it's attenuated by a factor of the dielectric constant. So the electric field is less than it would be in a regular parallel plate capacitor by a factor of k. So then we solve for the charge. So the charge, so the charge is kappa times the area of our capacitor times epsilon naught times the maximum electric field, which is 7 million volts per meter, and we end up with 199 microcoulombs. If you try to put any more charge on the capacitor than that, you're going to end up with dielectric breakdown. All right, now we're going to consider something totally different. What would happen if we had a charged capacitor? So here it is with plus Q on one plate and minus Q on the other, and we were inserting this dielectric between the plates. Do you think that the dielectric would be sucked in? Would you have to push it in, or would it not resist one way or the other? Think about that for a minute, and then we'll come back. Press pause. Well, the first thing you might think is that the dielectric becomes polarized, so the negative charge is attracted to the positive plate, and then the positive charge is attracted to the negative plate. So then as you insert this dielectric between the two plates, these things will be attracted and it will get sucked in. And that's what ends up happening for an isolated capacitor that's not connected to a battery. So let's see, the way you really find out what force you're exerting is by looking at the difference in the amount of energy that's stored in the capacitor. So here's our capacitor. Before we inserted a dielectric in it, it was 4.4 nanofarads, and after we inserted the dielectric and for that particular geometry, and I think we used mylar in it, and our capacitance was increased by a factor of 3.2. Well, if we look at the energy that's stored in the capacitor, remember Stalin's equation for the energy stored in a capacitor is Q squared over 2C. And here we have the capacitance is increased here. So we've got the same charge in both capacitors because it was an isolated capacitor that we're considering, and we're inserting this dielectric in between the plates. So charge remained constant, but then the one with mylar increased the capacitance, so we had less energy stored afterwards than before, so our change in energy was negative. Well, if our change in energy is negative, that means that we do negative work to insert this in between the plates. So that means that the force, it's actually getting sucked in, and we're exerting an external force in this direction, external force as the dielectric moves in there. We're exerting a force in the opposite direction that it's moving, and that's how we do negative work. And then it ends up with at a lower energy state than it was before we inserted the dielectric. Well, now let's consider a contrasting situation where we have the capacitor and we're going to allow it to be connected to a 9-volt battery the whole time. Do you think the same thing will happen? Well, you still have this induced charge, so you might think, well, it's still going to be attracted. But let's consider this problem from a point of view of energy. So here's the energy stored in the capacitor before we insert the dielectric, and then after we insert the dielectric, the potential is going to stay the same, but the charge is not going to stay the same. So the charge, we're putting in Q equals CV in for the charge there and squaring it, and then our new capacitance has that K factor in there, and then down here we already had a K factor, so we end up with the energy after we put the dielectric between the plates is going to be increased in this particular case. So if you have a battery, and the reason why that happens is because when you stick this dielectric between the plates, you're going to increase the capacitance, and you're going to, since you're still connected to the battery, you're going to call for more charge to be conducted from the battery. So that's why there's more energy stored in this case, where we had the plates connected to the battery. So if we end up with more energy after we insert the dielectric, then our change in energy, which is equal to E2 minus E1, is positive. So if it's positive, that means that you're doing positive work, so you better be pushing in the same direction as your displacement to do positive work. So that's why to insert a dielectric with the constant potential, it takes positive work. Well, we're already done. We found out why the electric field is reduced when an insulating material is inserted between the plates of a capacitor. We used John Lennon's equation to show why the capacitance is increased when a dielectric is inserted. We discovered how rare earth metals have been good for us, but not so good for others in developing countries. We used the dielectric strength of a dielectric to find out the maximum charge a capacitor can hold before it breaks down. We learned how to use the changes in stored energy to find out whether a dielectric gets sucked in or pushed out of a capacitor. And it depends on whether the voltage is constant or charge is constant.